The Probability of a Tennis Match by Olivia Ehrenberg from Roslyn Middle School. History. Probability originated from a disagreement between two famous mathematicians named Blaise Pascal and Pierre de Fermat in 1654. Antoine Gombard and Chevalier de Mere were French noblemen who created a game of throwing dice 24 times to clarify if it was smart to bet money on instances of at least one double six in the course of 24 rolls. Chevalier de Mere soon figured out that betting on a double six during 24 rolls of a die would be profitable. After this, he soon created a few principles of a new probability theory. Basic knowledge of probability. Probability is ratios that show how likely or unlikely an outcome would be. The ratio of probability could be any number or fraction from 0 to 1. The number could be converted into fraction, decimal, or even percentage form. If the probability is closer to 1, it is more likely to occur. If you evaluate your situation and end up with a probability greater than 0.5, then the event is likely to occur. If you have a 0.75 probability of winning an event and your friend has a 0.5 probability of winning the same event, then you have a higher chance of winning. The formula for any problem, if you want to find the probability, is the number of times it can occur over the total number of possible outcomes. For instance, let's say you want to find the probability of rolling a 2 on a die in one roll. You would evaluate it using these steps. Note that P stands for probability. So the probability of getting a 2 on a die is 1/6, which is about 17%. Compound events. Compound events are a combination of two or more simple events and therefore resulting in two or more outcomes. The total probability of all the outcomes of a compound event is equal to 1. Example of a compound event using tree diagrams and sample spaces. What is the probability of landing on heads on a penny and rolling a 6 on a die? Drawing a tree diagram and supplying a sample space will help you visualize this better when trying to solve the event's compound probability. A tree diagram is a drawing that shows all the possible ways the outcomes could turn out as. A sample space is a list of all the possible outcomes in an event. The sample space would be H1, H2, H3, H4, H5, H6, T1, T2, T3, T4, T5, T6. Note that H is heads and T is tails. The sample space would have the option of heads or tails since those are the outcomes of flipping a coin, and it would have the options of 1, 2, 3, 4, 5, or 6 because those are the possible outcomes of rolling a dice. A tree diagram is a very useful tool because it really gives a person a visual understanding of the situation or problem. So if you notice, you start and you flip a coin, and you have the outcome of heads or tails, and then after that you roll a die, so you have any option from 1 to 6. The probability of tossing a penny and landing on heads would be 1/2. After you toss the penny, you would then need to roll the die. The 6 possible outcomes of rolling a die are 1, 2, 3, 4, 5, and 6. The tree diagram shows you the different paths that you would need to take depending on what you land on and what you roll. Lastly, the final probability would be 1/2 because each outcome probability is 1/2 and 1/6, so you need to multiply those numbers to get 1/12. Experimental probability is a conducted experiment of the events in many trials. For example, let's say there were 5 kids in a classroom, A, B, C, D, and E. Each could ask to choose which flavor of ice cream was their favorite flavor. Since it's experimental, then you would have to conduct the event and ask all the 5 kids what their favorite flavor was. Theoretical probability is different because you are not experimenting. All you need to do is use prior knowledge about the situation and predict the outcome. The formula for finding the theoretical probability is the number of favorable outcomes over the number of possible outcomes. Sets. Sets are lists of gathered information such as the months of the year or the classes you take at school. Sets are typically displayed with Venn diagrams. The items in a set are called elements. When you create sets, each element is separated by a comma. For example, set X includes the days Saturday, Wednesday, and Tuesday. In roster notation, it would look like this. X equals Tuesday, Wednesday, and Saturday. The symbol E means an element of, so Saturday is an element of X. The opposite of an element is not being an element, so an element of set, and the symbol that represents that is the E with a line over it. So Monday is not an element of X. If set A includes Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, and Sunday, then set X is a subset of set A. A subset is a set where every element in the smaller set is in the bigger set. Since set X is a subset of set A, then the notation would be X is a subset of A. Universal sets are sets that contain all the elements in context. Each set of values is represented by a circle, and then overlapping elements will appear as an overlap circle between the two sets. The region where the two sets overlap is called the union. If you were to write this with notation, it would be A, U, B. This represents everything covered by both sets A and B, including their overlapping section. The union of this diagram would be represented by X is an element of A or X is an element of B. All the elements of both of them are 0, 1, 8, 9, 10, 12, 22, 32, 45, 52, 56, 61, 64, 66, 77, 88, 89, 99, 105. The elements that are in the overlapping section are called the intersections. They belong to both set A and B. The intersections in this example are 88, 12, 105, 99, and 52. The correct notation for the intersections are A and B. It is X is an element of A and X is an element of B. All the things that apply to intersections are 88, 12, 105, 99, 52. In a case where two sets do not overlap, they would be called mutually exclusive events. Sets would only overlap if they had the same elements. If all the elements are different, then they would be mutually exclusive. Since sets A and B both have none of the same elements, they're mutually exclusive. If you look at the bottom, in set A has bananas, blueberries, and strawberries, and B has none of the same because it has peaches, apples, and oranges, so there is no intersection. A die is rolled. What is the probability that there's a 3 rolled or a 6? The sample space is 1, 2, 3, 4, 5, or 6 because those are the possible outcomes. The probability of A is then getting a number on a die is 3, which is 1, 6, and the probability of B, which is getting a number on a die is 6, is 1, 6. The two outcomes do not overlap, so they're mutually exclusive. So the probability of A plus the probability of B is 2 6, which is equal to 1/3. So the probability of rolling a 3 or a 6 on a die is 1/3. Two-way frequency tables give you a way to display the probabilities for two different categories and a single group of people. One category is shown by rows and the other is shown by columns. Let's say you are surveying your class of 30 people and asking all the girls and boys if they like baseball or football better. This is the data collected. The total values for each event are 17 males, 13 females, 11 people like baseball total, and 19 people like football total. If you want to find the intersections, you must look at where the columns intersect. The number of males that prefer football are 9. The number of males that prefer baseball are 7. The number of males that got surveyed or people that prefer football are 26. A gender chosen randomly will be a female who likes baseball is 2/15, and a gender chosen randomly will be a female or a person who likes baseball will be 4/5. If you want to find the probability of each event occurring, it is right here. A male who likes baseball is about 23%. A female who likes baseball is about 13%. The total people who voted that like baseball are about 37%. Male who likes football is about 33%. Female who likes football is 30%. And total people who voted for football are 63%. The total males that voted are about 57%, and the total females that voted are about 43%. And all of that is equal to 100%, which is 1. The arrangement of objects in a specific order is called a permutation. Imagine there are 5 different people that want to be seated and there are 5 chair options. And how many ways could you put each person in a specific seat? There are 120 different ways to put the people in seats. There would be 120 different ways because there are 5 people A, B, C, D, E, and 5 chair options 1, 2, 3, 4, 5. The permutation would be 5 factorial, which equals 5 times 4 times 3 times 2 times 1. The factorial of a number is a function that multiplies by all the natural numbers below it. The notation for permutations is NPR. N is the total number of objects, and R is the total number of objects wanted. You would read it as blank objects taken blank wanted at a time. For toy trains, there are 5 objects taken 5 wanted at a time, so it's 5p5, which is equal to 120. The formulas for permutations are NPR, which is equal to n times n minus 1 times n minus 2 times n minus 3. All the numbers are being subtracted by r factorials. Factorials are decreasing whole numbers to 1. Way 2 is n factorial over n minus r factorial. Evaluate for P2, which is group of 4, choose 2. So way 1, it's 4 times 3, which is 12, and then way 2 is 4 factorial over 4 minus 2 factorial, which is 12 as well. Combinations. Permutations and combinations are very similar, but order matters in permutations and doesn't with combinations. For example, the permutation 1, 2, 3 is not the same as the permutation 2, 1, 3, but the combination of 1, 2, 3 is the same as 2, 1, 3 because the order does not matter. A combination is the choice of r things that you want from a set of n things without replacement, and order does not matter. The formula for combinations is n choose r, which is n factorial over r factorial times n minus r factorial. Dividing by r factorial will be necessary because you need to reduce the number of combinations since repetition is not important. So if you want to evaluate 5, choose 3, it would be 10. Binomial probability can be thought as a failed or accomplished outcome in an experiment which is repeated several times. The prefix bi means 2, so there are 2 different outcomes in conducting this experiment, which is failure or success. If the probability of success is p, then the probability of failure is 1 minus p. In this case, 1 equals 100%, so if you had a 40% probability, you would do 100% minus 40%, which equals 60% failure. When calculating the binomial probability, you must calculate the number of ways to select exactly r successes. The probability of success is p raised to the r power, and the probability of failure q raised to the n minus r power. N is the number of trials, r is the number of successes you want, p is the probability that the event will occur, and q is the probability that the event will not occur, which is 1 minus p. For example, if you roll a die 10 times, what is the probability that it will roll it 2 twice? So the number of trials is 10, the number of successes you want is 2, and then n minus r is 8. So the probability of rolling a 2 is 1/6, and probability of not rolling a 2, which is q, is 5/6. The combination of rolling a 2 is 10 factorial over 2 factorial times n minus 2 factorial, which is about 29%. Expansion. Probability with tennis. The rules of a tennis game are that you must win 4 points going from 0 to 15 to 30 to 40 to game. You can win a game in any of these ways: game love, game 15, game 30, and deuce to add, and then winning 40-40. You always have to win by 2, meaning that you cannot win if the score is game 40. You would have to go to deuce and add. In order to win a set, you must win 6 games by 2. So you cannot win a set 6-5. It would have to be 7-5 for the game to be over in that situation. The probability of winning a game if you have a 55% chance of winning since they have a similar skill level set as you. The probability of winning a game love is 0.55 to the fourth, because you would do a point for me, another point for me, another point for me, and another point for me, since you're winning 4 points. So that is about 9%, which is a very low chance. If you're winning a game 15, you're pointed towards 1 point and you score 4. So it's 4, choose 1. Combinations would make sense in this situation because it doesn't matter the order. It just matters that you win 4 points before your opponent wins more than 1. The probability of winning a game 15, there's 4 ways, which is times p to the fourth because you win 4 points, times 1 minus p because your opponent wins 1 point. You would do 4 times p to the fourth times 1 minus p, which is about 16% chance. Winning a game 30, is 5 choose 2 because there's 10 ways times p to the fourth because there's 4 points times 1 minus p squared because you're losing 2 points. That is an 18% chance. The probability of getting to deuce is 6 choose 3. There's 20 ways times p to the third, which is how many points you win, tells you what the exponent is, times 1 minus p cubed since you're losing 3 points. That is about a 30% chance. Winning deuce. If you get to the point where your game's all tied at 40-40, then you must win deuce and the add point to win the game. You either win the first 2 points or you lose the first 2 points, which is p squared, or 1 minus p squared, which means that you lose. When you win after return to deuce, the probability of returning to deuce, which is each person wins a point, which is 2 times p times 1 minus p. You could either win and then your opponent wins, or your opponent wins and then you win, which is returning to deuce both ways. So what you would do is you do 1 minus 2 times p times 1 minus p, which is equal to p squared, which is p squared divided by 1 minus 2 times p times 1 minus p. 20p to the fifth times 1 minus p cubed divided by 1 minus 2 times p times 1 minus p. When you plug in the numbers, you would get about an 18% chance of winning with deuce right away. If you want to find the total probability, you would add up all the subs, which will give you about a 62% chance of winning. Probability is used to help people know their chances of achieving something or failing. It helps people make decisions in life, and being able to have knowledge about this topic can really benefit your well-being. After experimenting on many different examples of real-life situations of probability, I can conclude that the more complicated scenarios use harder and more complicated strategies that can be helpful throughout life. Now that you know how to solve all different examples of probability, go try some. Thank you for watching.